Okay friends, the last lecture we have seen what is the meaning of a vector space and what is the meaning of a subspace and how to decide whether a given subset of a vector space is a subspace or it is not a subspace. In the next part, our aim is just to define what is the dimension of a vector space. But before defining dimension of a vector space, we will have to see few things, and that I shall go slowly and slowly towards defining the dimension of a vector space. So, for this purpose, first of all we should be aware what is the meaning of linear combination of the elements of a vector space. So, suppose that V is a vector space and you are having V1, V2, Vk, k elements in the vector space. Then what is the meaning of linear combination? So, if C1, C2, C3, Cn they are real numbers, then C1 plus V1, C1 into V1 plus C2 into V2 plus C3 into V3 and so on and so forth plus Ck into Vk. This is again a vector and this is an element of V, and that we are calling here V, small v. Then this V is called linear combination of V1, V2, Vk. See once more. If V1, V2, V3, Vk are elements of V, then the linear combination of V1, V2, Vk means C1 into V1 plus C2 into V2 plus C3 into V3 and so on and so forth plus Ck into Vk. This is called linear combination of the elements V1, V2, Vk. Simple meaning. Now, suppose that V is a vector space and S equals V1, V2, V3, Vk be a subset of the vector space V. Then second, we shall define what is the meaning of span of the set. So, what is the span of the set? We shall denote as S within the square bracket S. That is a standard notation. If you are writing S within the square bracket, that is the meaning that span of S we are talking about. So, span of S is the set of all possible linear combination of the elements of S. Simple meaning. Span of S means set of all possible linear combination of the elements of S. That is, span of S is the set of all elements of the type C1 into V1 plus C2 into V2 plus Ck into Vk, where all these C1, C2, C3, Ck are real numbers. So, this is called span of S. Okay. So, see here whether 0 element is in the span of S or no. 0 element whether it is in span of S or no, that is very important. What is the meaning of span of S? Set of linear combination of the elements of S. So, S is having the elements V1, V2, Vk. Okay. And linear combination, can you see here, if you take C1, C2, Ck all 0 means what? 0 into V1 plus 0 into V2 and so on and so forth plus 0 into Vn, 0 into Vn or 0 into Vk. See here all C1, C2, Ck are taking to be 0. So, this is also a linear combination of the elements of S, and that is 0 into V1 plus 0 into V2 plus 0 into Vk, that is equal to 0, and this shows that 0 is an element of the span of S. Remember, 0 is not in S. S is only a subset of V. V is a vector space. S is, I am not saying that it is a subspace, it is simply a subset. S is any subset of V, and span of S is the set of all possible linear combination of the elements of S. And just now we have seen here that 0 element is in the span of S. Therefore, span of S is always non-empty. In the short while you shall see that span of S is always a subspace of V. I shall repeat once. Look at here, V is a vector space, fine. Then the meaning of span of S means the set of all possible linear combination of the elements of S, simple meaning. and just now we have seen that 0 is always in the span of S, because 0 can be expressed as 0 into V1 plus 0 into V2 plus 0 into V3 and so on and so forth plus 0 into Vk. So 0 is a linear combination of the elements of S, therefore 0 is in the span of S, and hence span of S is always a non-empty set. And not only this, span of S is in fact a subspace of V. Remember, S is not a subspace, S is only a non-empty set. But span of S, I am saying that it is a subspace, always a subspace. Whether S is a subspace or not a subspace does not matter at all. If S is a subspace, fine, span of S will be a subspace, but even if S is not a subspace, S is simply a subset of the vector space V, then span of S is always a subspace. Why? Because first property we have seen that span of S is non-empty because 0 element is there. Then we shall see that this span of S is closed under vector addition as well as scalar multiplication. But before this, let us see some example of a span of S. Then we shall show that span of S is always a subspace. So look at here, V is R3 and S is the set of two elements consisting of 1 0 0 and 0 0 1. So S is a subset of R3. Remember, this S is not a subspace because 0 element is not in S. Here 0 element is not in S. 0 element is not in S, therefore S is not a subspace. S is simply a subset of R3. But span of S, what is the span of S? Span of S means set of all possible linear combinations. Means what? Set of all possible linear combinations means A into 1 0 0, that is the first element, plus B into 0 0 1. So what is this one? A into 1 0 0. So this is A 0 0 plus B into 0 0 1. So this is your 0 0 B. And if you are going to add, you are going to get here A 0 B, A 0 B. So in fact, what is this one? In fact, look at here, this is your A 0 0 plus 0 into B 0 and 0 0 B. So if you add, you are going to get here A 0 B. So span of S, it is the set of all triplets of the form A 0 B, where A and B are any real numbers, but the second entry, that is must be 0, must be 0. So A 0 B. So for example, 1 0 1, it is an element of the span of S. 2 0 minus 3, 2 0 minus 3, it is an element of the span of S, because A and B are any real numbers and second element must be 0. So this is span of S. Now we are going to see here that if S is a non-empty subset of a vector space, then span of S is always a subspace. Whether S is a subspace or S is not a subspace does not matter at all. Span of S is always a subspace. I have already explained you that span of S is non-empty because 0 element is inside the span of S, and if you take any two elements from the span of S, then see that their sum must be in the span of S. So I am taking U in any element, U and V any element in S. If U and V are in S, therefore U is the linear combination of the sum of the elements of S, sum of the elements of S. Similarly, V is also a linear combination of the elements of S. Therefore, U plus B, it will be also a linear combination of the elements of S. Therefore, U plus B will be inside S. So if U is this, then if you look at here V, so take V is also a linear combination of the elements of S. Take U plus V, you will see that it is a linear combination. Finally, it is a linear combination of the elements of S. Therefore, U plus V is inside the span of S. Similarly, if U is here, if you multiply with any scalar alpha into U will be alpha into C1, alpha C1 into U1 plus alpha C2 into U2 and so on and so forth, plus alpha Cm into Um. And alpha C1, alpha C2, alpha Cm, they are also scalars. Therefore, this alpha into U is also a linear combination of the elements of S. Therefore, span of S is closed with respect to scalar multiplication also, and hence span of S is a subspace. So, these two property you can see yourself that first of all span of S is non-empty, we are supposed to show, although I have not shown on the on the slide. I have explained that 0 is an element of span of S always. Second is that 0 is closed, u plus v, look at here, these are the again elements, these are the linear combination of the elements of S. Therefore, u plus v is again the inside the span of S. Remember here one very important part, whether I do mention or I do not mention, the meaning of linear combination means always finite linear combination. Finite linear combination means take finite number of elements from the set S, then make a linear combination, that is called finite linear combination. So, we do not talk about infinite linear combination, we shall talk about linear combination means always it is a finite linear combination. So, look at here u plus v, it is a finite linear combination of the elements of S, therefore, u plus v is inside S. Again second property is that this span of S is also closed under vector addition. As vector addition we have seen under scalar multiplication. So, if A is any scalar, then A into u, see that it is again a linear combination of the elements of S, and therefore, A into u is again inside span of S, therefore, span of S is a subspace of V. This is a very important result. Let us take one example where we are taking the vector space as P2. P2 means the set of all polynomials of degree less than or equal to 2. P2 means set of all polynomials of degree less than or equal to 2. And S, look at here, what is S? S consists of 3 polynomials. First polynomial is x square plus 1, it is a polynomial of degree 2. Second is x minus 1, it is a polynomial of degree 1, it is therefore it is less than or equal to 2. Third is x square plus x, it is a polynomial of degree 2. So, S it is a subset of P2, S it is a subset of P2. Question arises whether this S spans V or no, S spans V or does not span V. Remember here, first of all, S, what is the meaning of S spans V? V is a vector space. S spans V means span of S must be equal to V. Span of S must be equal to V. But just now we have seen span of S is always a subspace of V. Span of S is always a subspace. When it is a subspace, it is also a subset. A subspace must be a subset. But when it is a subset, it is not a subspace. So, when span of S, it is a subspace of V, therefore, it is also a subset. So, S spans V means span of S is equal to V, and when span of S is equal to V means how to prove that two sets are equal. The set A is equal to the another set B means that A is a subset of B as well as B is also a subset of S. That is the meaning the two sets are equal. So, if V is equal to span of S, it means that span of S must be a subset of V and V must be also a subset of the span of S. Okay, if both the properties are satisfied, we shall say that span of S is equal to V, meaning thereby that S spans V. But out of these two property, look at here, this property is always satisfied. Why it is always satisfied? Because span of S is always a subspace of V. Therefore, span of S is always a subset of V. Therefore, S spans V means span of S is equal to V, meaning thereby that V is a subset of S. V is a subset of span of S. Only this part you will have to prove that V is a subset of span of S. Other is satisfied automatically. Therefore, S spans V means we shall simply say that V is a subset of span of S. The moment you are proving that V is a subset of span of S, it will automatically imply that V is equal to span of S, therefore S spans V. Then what is the meaning that V spans S? Means V is a subset of span of S. When V is a subset of span of S, V it is a subset of span of S, means what is the meaning of this one? A is a subset of V, means every element of A is an element of V. So, V is a vector space which is a subset of the span of S, meaning thereby that every element of the vector space V is an element of the span of S. So, every element of V is an element of the span of S. What is the meaning of that again? It means that every element of V is an element of the span of S. An element of span of S means linear combination of the elements of S. So, therefore, if every element of V can be expressed as the linear combination of the elements of S, we shall say that V is a subset of the span of S, that is S spans V. So, see once more finally what I am saying here. What is the meaning that S spans V means? S spans V means span of S is equal to V. Span of S is equal to V means span of S is a subset of V, that is satisfied always. Therefore, we shall not check this part, only we shall check that V is a subset of span of S. V is a subset of span of S means every element of V is an element of span of S. Every element of V is an element of span of S means every element of the vector space must be expressed as the linear combination of the elements of S, that will imply that S spans V. Okay. So, what is the final conclusion? V spans S, not sorry, S spans V. S spans V means every element of V must be expressed as the linear combination of the elements of S. Simple. Fine. So, let us see this example whether S spans V or no. So, what is the meaning that every element, in fact this is your Px. So, every element of V, what is V? V is the set of all polynomials of degree less than equal to 2. So, every polynomial of degree less than equal to 2, if it can be expressed as the linear combination of elements of S, it will imply that S spans P2. If it is not possible, it will imply that S does not span P2. So, see I am saying that suppose Px belongs to the span of S, Px belongs to span of S, then Px must be expressed as the linear combination of the elements of S. This is the linear combination, alpha into x square plus 1, these are x square plus 1, x minus 1 and x square plus x, they are the elements of S. So, see here that I am saying alpha into x square plus 1 plus beta into x minus 1 plus gamma into x square plus x. And what is this one? Px. Px is any polynomial of degree 2, any polynomial of degree 2. So, if this is meaningful, meaningful means every polynomial of degree 2, if a or any polynomial of degree 2 can be expressed as the linear combination of these 3 polynomials, these 3 elements of S, see whether it is possible or it is not possible. If it is possible, we will have to prove. If it is possible, then we shall say that S spans V. If it is not possible, then we shall say that S does not span V. Remember, LHS is a polynomial of degree 2. RHS is also a polynomial of degree 2. When 2 polynomials are equal, LHS is a polynomial, RHS is a polynomial, both polynomials are equal when 2 polynomials are said to be equal if the powers of coefficient of equal powers of x must be same. 2 polynomials are said to be equal if and only if coefficient of equal powers of x must be same. It means what? In the LHS, coefficient of x square is a. In RHS, say what is the coefficient of x square. So, a must be equal to this. So, again in LHS, coefficient of x is b. So, see what is the coefficient of x in RHS. And what is in LHS? C is a constant. See what is the constant term in RHS. See these 3 are equal or they are not equal. So, see what we are going to get from here. We shall use here just the definition of equality of 2 polynomials, then we are going to get 3 equations. Okay friends, I have explained what is the meaning of equality of 2 polynomials. Okay, let me write once more very clearly: a into x square plus b into x plus c, that is your RHS, sorry LHS part, and see what is RHS. RHS is, first you equate what is the coefficient of x square, coefficient of x square. First one, the coefficient of x square is alpha plus gamma. alpha plus gamma. Second term, if you look at here, coefficient of x you collect together, coefficient of x is beta plus gamma, beta plus gamma. Then the constant term are alpha minus beta, alpha minus beta. So look at here, these two polynomials will be equal if and only if this alpha plus gamma must be equal to a, coefficient of x square must be equal to coefficient of x square. Secondly, that coefficient of x, that is beta plus gamma, must be equal to b. Third is that alpha minus beta must be equal to a, constant term c. So whether these, what is the meaning that these two polynomials are equal? We have said that coefficient of equal parts of x must be same, and from here we are getting three equations: alpha plus gamma is equal to a, beta plus gamma is equal to b, and alpha minus beta is c. But whether it is possible or it is not possible, that we will have to see. It means what? Look at here. Remember our first two lectures. Whether this system is consistent or it is not consistent. If it is not consistent, means it does not have any solution. If it does not have any solution, means this LHS is equal to RHS is not meaningful. And therefore, S will not span P2. And C, if this system is consistent, it will imply that S spans P2. So how to check that this system is consistent or it is not consistent? Okay, do you recall? So we shall make one matrix, coefficient matrix, alpha, beta, gamma, they are unknowns, and a, b, c are known. So coefficient of alpha is 1, beta is not, so 0, coefficient of gamma is 1. In the second equation here, coefficient of alpha is 0, beta 1, gamma 1. Third is here alpha, coefficient of alpha 1, coefficient of beta minus 1, there is no gamma, so 0. And if you look at here, the augmented matrix, this is your A, B, C. This is our augmented matrix. Okay. So if now we want to change this matrix into row reduced echelon form. So here it is already 1, here it is 0. So you want to make this one to be 0. How to make this element to be 0? This one you want, this one you want to be make to be 0. So therefore, how we shall make to be 0? Can you see here? Means if you, can you change the R3 row, third row by R3 minus R1? Then you see that what you are going, first will remain as it is 1, 0, 1 and A, second is 0, 1, 1, then R3 minus R1 means 1 minus 1, that is 0, 0, the minus 1, 0, minus 1, then 0, minus 1, minus 1, then C minus A, C minus A, here it remains B. At this stage it is not in row reduced echelon form. So if you see here, if you are going to, again you want this one, this element you want to be 0. So how this element will be 0? Adds R2 to R3. What you will get here? Now replace R3 by R3 plus R2. R3 plus R2. See what you are going to get. 1, 0, 1, A, 0, 1, 1, B. Adding, second row we are adding to third. So 0 plus 0, that is 0. 1 minus 1, that is 0. 1 minus 1, that is 0. And then we are getting here C minus A plus B. Now look at here, this is very important. So this is 0, 0, 0. So that is 0 into alpha plus 0 into beta plus 0 into gamma is equal to C minus A plus B. So this shows that what? C minus A plus B, the moment it is different from 0, remember A, B, C, they are any real numbers. This A, B and C, they are any real numbers. Therefore, C minus A plus B need not be always 0. The moment C minus A plus B is different from 0, therefore, the system is inconsistent. 0 cannot be equal to a non-zero quantity. or we can see that row rank of the coefficient matrix A is 2 and row rank of the augmentary matrix is 3, both are not equal, therefore the system is inconsistent. And when the system is inconsistent, it will imply that S does not span P2, that is every element of P2 cannot be expressed as the linear combination of the elements of S, thus S does not span P2. So friends, we have seen what is the meaning of span of a set S. Now we are ready to see what is the meaning of linearly independent set and linearly dependent set. Slowly and slowly we are moving to define dimension of a vector space. See what is linearly independent set and linearly dependent set. Idea or the concept must be very, very clear for linearly dependent and linearly independent. I am saying that suppose V is a vector space and V1, V2, Vk, they are elements of V. I am saying that these vectors are linearly independent. Remember that LIE has been used for linearly independent and LD has been used in the lecture everywhere for linearly dependent. So these vectors V1, V2, Vk are said to be linearly independent if you make a linear combination of these elements, that is C1 into V1 plus C2 into V2 and so on and so forth plus Ck into Vk is equal to 0, and if it implies that Ci is equal to 0 for all I, then we say that V1, V2, Vk are linearly independent. See what is the meaning? It is once more here, C1 into V1 plus C2 into V2 and so on and so forth plus Ck into Vk is equal to 0. So if C1, C2, C3, Ck are 0, then it is always 0 is equal to 0. So remember here, Ci is equal to 0, C1 equals 0, Ct equals 0 and Cn equals 0, it is always a solution. We are interested, is there any solution which is different from 0? If no, means what? If this equation has only 0 solutions in C1, C2, Ck, so only C1 equals 0, Ct equals 0 and Ck equals 0 is the only solution, there is no any other solution except this, then we say that V1, V2, Vk are linearly independent. And if there is any other solution which is different from 0, the moment I am saying that there is any other solution different from 0 means non-zero solution. The moment we are getting a non-zero solution, it will imply that V1, V2, Vk are linearly dependent. So if you make a linear combination C1 into V1 plus C2 into V2 and so on and so forth plus Ck into Vk is equal to 0, solve this equation. If we are getting only 0 solution, no any other solution, then we shall say that these vectors V1, V2, Vk are linearly independent. And if there is any other solution which is different from 0, then we shall say that these vectors V1, V2, Vk are linearly dependent. Or another way of saying linearly dependent set, that suppose these vectors V1, V2, Vk are said to be linearly dependent if there exists scalars C1, C2, Ck not all 0 at a time, such that C1 into V1 plus C2 into V2 plus so on and so forth plus Ck into Vk is equal to 0. So look at here, there is at least one C1, C2, there is at least one Ci out of these C1, C2, Ck which is different from 0. Out of these C1, C2, Ck, if there is at least one Ci which is different from 0, but their sum is 0, C1 into V1 plus C2 into V2 plus Ck into Vk is 0, that will imply that V1, V2, Vk are linearly dependent. Let us see some examples. A non-zero vector is always linearly independent. Why a non-zero vector is always linearly dependent? Suppose I am saying that U, it is a non-zero vector and alpha is any scalar. So there is a set which consists of a single vector and that is non-zero. So if alpha into U is equal to 0, then we have seen that either alpha is 0 or U is 0. but we are taking that U is different from 0. A set consisting of a single element which is different from 0 is always linearly independent. The reason is that suppose U is a non-zero element, then alpha into U is equal to 0 will imply that alpha is 0 because U is different from 0. Therefore, alpha equals 0 is the only solution, and therefore U is linearly independent, or the set consisting of a single non-zero vector is linearly independent. Second is also very important. Second is zero vector is always linearly dependent. Zero vector is always linearly dependent because if you make a linear commission, 1 into 0 is equal to what? 1 into 0 is equal to 0. Look at here, the scalar 1, that is a non-zero solution. 1 into 0 is equal to 0. So, C1 into U is equal to 0, and C1 is equal to, if C1 is non-zero, then it will be linearly dependent. So, we see here that 1 into U is equal to 0, that shows that the set consisting of zero vector is always linearly dependent. And non-empty set by convention we shall take to be linearly independent. Non-empty, sorry, a empty set phi is always considered to be linearly independent because there is no element there, so nothing is to do. So, just it is a convention that empty set phi will be always considered to be linearly independent. So, see the second part, that zero vector is always linearly dependent, it is very useful. If there is any set which consists of a zero vector, then you can say immediately that it is linearly dependent. The whole set is linearly dependent. Okay. Why? Let me explain. Why any set consisting of zero vector is linearly dependent. I am saying that suppose V is a vector space, V it is a vector space, and I am saying that S it is a set consists of some elements, one element is 0, other is U1, U2 and UN. Okay, whether the moment S contains zero vector, I am saying that it is linearly dependent. Why it is linearly dependent? Because if you take here, I can say that 1 into 0 plus 0 into U1 plus 0 into U2 and so on so forth, plus 0 into UN plus 0 into UN is equal to 0. Look at here, this is a linear combination. 0, U1, U2, UN, they are the elements of S. This 0, 0, U1, U2 and this UN, they are the elements of S. See that I have made a linear combination. C1 into, in place of C1 it is 1, C2 is 0, C3 is 0, C4 is 0 and Cn plus 1 is also 0. So, look at here, there is one scalar, this one which is different from 0. So, look at here, this is equal to 0. So, 1, 0, 0, 0 it is a solution. There is a one Ci which is different from 0, one C1 which is different from 0. Therefore, this set S is linearly dependent. S is linearly dependent. S is linearly dependent. Why? Because what I have explained, that if C1 into U1 plus C2 into U2 and so on so forth plus Cn into Un is equal to 0, if there is any Ci which is different from 0, it will imply that U1, U2, Un is linearly dependent. And if all Ci's are 0 and there is no any other solution, it will imply that U1, U2, Un are linearly independent. Therefore, any set consisting of a zero vector is always linearly dependent. So, remember, the moment any set consists of a zero vector, it will imply that the given set is linearly dependent. Let us see one example. I am taking here first element E1 is 1 0 0, E2 0 1 0, E3 0 0 1. The set S is consisting of these three vectors E1, E2, E3. And I am saying that this is linearly independent, this is linearly independent in R3. Why it is linearly independent in R3? make a linear combination first of all and make it equal to 0. So, alpha 1 into E1 plus alpha 2 into E2 plus alpha 3 into E3 is equal to 0, and this 0 is an element of 0 vector of R3. When it is 0 vector of R3, then it is of 0 0 0. So, see what is here, alpha 1 into E1, E1 is 1 0 0. So, therefore, alpha 1 into E1 is alpha 1 0 0, alpha 2 E2 is 0 alpha 2 0, alpha 3 3 0 0 alpha 3. See that you are going to get here sum is alpha 1 alpha 2 alpha 3 is equal to 0 0 0. Therefore, alpha 1 is 0, alpha 2 is 0, alpha 3 is 0. So, you are getting only 0 solution, there is no any other solution, and therefore, this shows that this set is consisting of these 3 elements E1, E2, E3 is linearly independent. The set S is linearly independent. Look at this set. This set is linearly dependent. Why this set linearly dependent? First of all, look at here, V1 is so take linear combination and solve this one, you will get a non-zero solution. In fact, what is this one? V1 is equal to 1 2, V2 is your 5 0. So, one is a scalar multiple of the other, means what? So, let me make one is line, this is your A into V1, A into V1 plus V into V2 is equal to 0. This 0 means this is 0 element of R2, therefore, this 0 means it is 0 0. So, what you are going to get here? This implies that A into V1 is A and this is your V. So, first element you are going to get here A plus 5B. Other element is 2A plus this B into 5 plus 10 into B is equal to 0 0. So, see that A plus 5B is 0 and 2A plus 10B is also 0. So, 2A plus 10B is 0 is same as A plus 5 is 0. So, A plus 5B is 0, you are having one equation, 2 unknowns, or you will get only a straight line. So, every point lying on this line will be a solution. Therefore, it has infinite number of solutions. The moment it has infinite number of solutions, of course, A equals 0, B equals 0, it is a solution. But there are infinite number of other solutions which are different from 0. Therefore, this is linearly dependent. Let us see this set S is the set consisting of 3 polynomials P1, P2, P3, where P1x is given by x square plus x plus 2, P2x is given by 2x square plus x, and P3x is also a polynomial of degree 3, 3x square plus x plus 2. So, whether it is linearly independent or it is not linearly independent, let us make a linear combination and then set it to be equal to 0 and see whether what is the solution of this one. So, you shall say that A into P1 plus B into P2 plus C into P3 is equal to 0, then you shall see that what happens. So, this is your linear combination A into P1 plus B into P2 plus C into P3 is equal to 0. This is your linear combination. Again, what is the meaning of RHS? This 0 it is a 0 polynomial, this is a 0 polynomial. 0 polynomial means a polynomial is said to be 0 when each coefficient of x must be 0. So, see that here coefficient of x is square, coefficient of x, coefficient of and the constant term must be equal to 0. What is the coefficient of x square? Coefficient of x square is here, first one coefficient of x square is a, one x is a plus 2b plus 3c. This is the first equation, a plus 2b plus 3c is equal to 0. This one a plus b plus c, this is the coefficient of x. This is your a into x plus b into x plus c into x, that is a plus b plus c is 0. This is the coefficient of x. Constant term 2 into a plus 2 into c, 2a plus 2c is equal to 0. Solve these 3 equations, 3 unknowns. So, look at here a plus c, here this will imply, the last equation implies that a plus c is 0, a plus c is equal to 0. The moment a plus c is 0, look at here from the second equation, a plus c is 0, therefore b must be 0. Okay. So, therefore b is 0. When b is 0, then you see from here a plus 3c is 0. So, a plus 3c is 0 and a plus c is also 0. See from here that c is 0, the moment c is 0, therefore a is 0. So, a is 0, b is 0 and c is 0, this is the only solution, there is no any other solution. Therefore, the set S consisting of these 3 polynomials P1, P2, P3, this set is linearly independent. Look at another example quickly. again S is the set of all polynomials of degree less than equal to 2. So, S is again a subset of P2, the set of all polynomials of degree less than equal to 2. See whether it is linearly dependent or linearly independent. We shall make a linear combination and to be equal to 0. This is 0 polynomial a into 1 minus x plus b into x minus x square plus c into 1 minus x square is equal to 0. So, see that here coefficient constant term is a plus c, coefficient of x is b minus a, and coefficient of x square is minus of b plus c, and this is equal to 0. Therefore, a plus c is 0, b minus a is 0 and b plus c is 0. Solve these three equations, see what happens. A plus c is 0 and b minus a is 0 and b plus c is also 0. So, look at here, b minus a is equal to 0, this will imply that b is equal to a. Second equation implies that b is equal to a. And from the second, and from b plus c is equal to 0, therefore, from here the last equation you can see that c is equal to minus b and minus b is equal to minus a. Fine. And from first equation see that c is equal to minus a, c is equal to minus a, c is your minus a, okay, c is your minus a. So, c is minus a, b is a, and therefore, if you see that if you give any value of a, you will get infinite number of solutions. So, this shows that this three equations, three unknowns, it has infinite number of solutions. So, let me go to the next slide, then it will be much more clear. These three equations in three unknowns, see that you are going to get b is equal to a and c is equal to minus a, where a is any arbitrary real number, it will give a solution. So, if give any number of any real value of a, see if a is 1, then look at here, b is 1, c is minus 1. So, a is 1, b is, c is minus 1 and a equals 1, it is a solution. Change a is equal to 2, again you will get corresponding b and c, it is a solution. So, for every real number a, you will get corresponding value of b and c, therefore, we are getting infinite number of solutions, even non-zero solutions. If of course, if a is 0, then b and c both are 0. So, 0, 0 is always a solution, but there are here infinite number of other solutions which are different from 0. Therefore, the given set S is linearly dependent. Now, we are in a position to define what is the meaning of basis and dimension. Okay. So, before defining dimension, again we should be aware what is the meaning of basis, then we shall know what is the meaning of a dimension. Basis means, suppose first of all V is a vector space and S is a subset of V, then S is called a basis of V if and only if two conditions are satisfied. First is that S must be linearly independent, and then span of S must be equal to V. These two things we have seen very clearly, what is the meaning of linearly independent and what is the meaning of S spans V. So, this set S is called a basis of the vector space V if and only if S should be linearly independent as well as S must span V, that is span of S is equal to V, means that every element of V must be expressed as the linear combination of the elements of S. If these two properties are satisfied, then S is a basis of V. Then what is the meaning of dimension now? The moment we know what is the meaning of basis, dimension of a vector space means, see what is the number of elements in the basis. Number of elements in the basis of a vector space is called dimension of the vector space. So, clear, dimension of a vector space means number of elements in the basis of a vector space. And then what is the meaning of finite dimensional vector space? Finite dimensional vector space means dimension is finite. Dimension is finite means number of elements in the basis is finite. If the number of elements in a basis of a vector space is finite, then we say that the vector space is finite dimensional. And of course, the number of elements in the basis will be equal to the dimension of the vector space. Look at here the first example, S. I am taking here, it is 1 0 0 1, it is a subset of R2, okay. And we have seen that 1 0 0 0 1 0 0 0 1 is linearly independent. So, 1 0 0 1 is also linearly independent, because if you take A into 1 0 plus B into 0 1 is equal to 0 0, then you see that A is 0 and B is 0. It is the only solution. There is no any other solution. Therefore, the set S is linearly independent. Not only S is linearly independent. Why S spans R2? Why S spans R2? Because S spans V also. Why S spans V? And V is R2. So, if you take any element in R2, any element in R2 is always of the form X and Y. It is any element of R2, and this can be written as, look at where, X into 1 0 plus Y into 0 1, Y into 0 1. And what is 1 0 0 1? They are the elements of the set S. They are the element of the set S. Therefore, every element of R2, this is XY, this is any arbitrary element of R2. Every element of R2 has been expressed as the linear combination of the elements of S. Remember, what is the meaning of S spans V means? Every element of V must be expressed as the linear combination of the elements of S. And that is the thing here. Every element of R2 has been expressed as the linear combination of the elements of S. Therefore, S spans R2 and S is linearly independent. Therefore, S is a basis. S is a basis of R2. And what is the number of elements in S? 1 0 is one element, 0 1 is another element. So, it has only two elements. Therefore, dimension of R2 is dimension of R2 over the field of real number is 2. Dimension of R2 is 2. Similarly, you can see that 1 0 0, 0 1 0, 0 0 1, it is a basis of R3, because this set is linearly independent and any element in R3 is of the form XYZ, and XYZ can be expressed as X into 1 0 0 plus Y into 0 1 0 plus Z into 0 0 1. Therefore, this set S spans R3 also, and hence S is a basis for R3. When S is a basis of R3 and S contains 3 elements, therefore, dimension of R3 is also 3. Similarly, you can see that dimension of Rn over Rn is n. Exactly similarly way, this is Rn. You are taking here n elements, X is n triplets, E1 is 1 0 0, E2 is 0 1 0, and so on and so forth, En is 0 0 0 1. You can see that again this is linearly independent, and every element of Rn can be expressed the linear combination of E1 E2 En, and that so that S spans Rn, and hence E1 E2 the set S consisting of E1 E2 En is a basis. When it is a basis, therefore dimension of Rn is n. Again you can see that the set consisting set 1x, it is a basis for P1. P1 is a set of polynomials of degree less than equal to 1. Why it is linearly independent? Because if you make it linear combination A into 1 plus B into x is equal to 0, A into 1 plus B into x is 0, this is a 0 polynomial, therefore A must be 0, B must be 0, therefore this set is linearly independent. And again S spans P1. P1 is the set of polynomials of degree less than equal to 1. So, any polynomial of P1 is a linear combination of 1 and x, because P1 means any polynomial of degree 1 is of the form A plus Bx. Therefore, S spans P1 also, and hence S is a basis for P1, and dimension of P1 is 2. Look at the dimension of P1. P1 is a polynomial of degree less than equal to 1. Dimension of P1 is 2 because S contains 2 elements. S is a basis and it contains 2 elements 1 and x. Similarly, 1x and x square, it is linearly independent because A into 1 plus B into x plus C into x square is equal to 0. A 0 polynomial will imply that A is 0, B is 0, C is 0. S is linearly independent. Again, any element of P2 will be the linear combination of 1x and x square. Therefore, S spans P2. Therefore, S is a basis, and hence dimension of P2 is 3. Similarly, dimension of Pn will be n plus 1, where S is 1x, x square, x to the power n. This is a basis for Pn, and these bases are called standard basis or natural basis. Suppose if V is the 0 space, if V is 0 space, it is always linearly dependent, it cannot have any basis. If it cannot have any basis, it cannot have any element, and therefore dimension of V is 0. Dimension of V is 0. Okay. So, dimension of a 0 space is always 0. I shall stop here, then I shall in the next class I shall start some results based on basis and dimension, and then linear transformation. Thank you.